these, hand them around. Some of these back. Some of these back. And some of these thrown around. Some back here. You can hand these across if you want. Oops, there we go. Good. Okay, good morning, everyone. Happy Friday. Woo, Friday. Nah, not so much. Okay. All right. So the first compiler assignment went out the Wednesday evening, Thursday morning-ish. And so today I want to finish off what we started talking about on Wednesday with defining let expressions that introduce variables and let us look up variables. It's a big part of the programming assignment. In this case, in class, I'm going to go through something very close to how you're going to implement this for the programming assignment itself. I think it's really useful at the beginning to do this. So we're going to talk about let bindings in class that only have a single variable defined. In your homework, you'll be writing them with multiple variables defined with a couple of extra rules. So on the worksheet that I handed out, this is the code that's on the right-hand side of the part with all the OCaml implementation. I filled in the implementation for EID here because what I want to do today in class is sort of set up half of this, which is what is it going to look like to look up one of these identifiers in an expression. What does it mean to look up the name of a variable? What does that do? And we'll use that to understand what let should do in order to set things up for EID to work. So I want to start by getting you to read this code, and I want to do that by asking these two questions on the right-hand side. So let's start with this question. Just what I want you to do is read the code. You should be able to read through this and see what will happen if we call this expert instructions. Oops, I have an argument order mistake. I just realized on this. The expression should be first. Sorry. I had this different in my code than I had right here. So this expression is supposed to be the first argument to this because the expert instruction says an expression and then a number and then this environment thing. So these should just be the first argument here. So answer this first question. What instructions will we get from running this expert instructions on EIDY with this as of yet unexplained SI parameter that's an integer is 0, and as of yet unexplained env parameter, which is this list that says x1, y2. So I want you to read the code to understand this and answer. So answer this first question up here. 10 more seconds. Five, four, three, two, one. Okay, talk this over for a minute. Answer to this part. I don't have any more up here. There should be some in the back, like in that back corner or something. Yeah. I can take the extras. Okay, click in again. The results of talking about it. Okay. Okay. Five, four, three, two, one. Okay. All right. Cool. Let's talk about this for a minute. So what's happening here in the EID case is, well, we know we're going to get into, the case I already highlighted that has EID as the match. We're going into expert instructions. We're looking at an ID expression. And so the OCaml variable x is going to get the string y, because that's the thing inside the EID. And then the next thing that happens is we're going to process this call to find. Find is a reasonably well-named function. Find takes in one of these env things. Again, I haven't said what an env is. I'm just having us read this code so we can see what happens and then ascribe some meaning to these pieces. So find says it's going to take one of these envs. It's going to take a string, and it's going to give back either none or some integer. And what it does is it basically iterates through the list that was given to it and stops if it finds the particular string we passed in to look for. So this is just linear search through a list that's mapping from strings to numbers. That's really what this env thing is, right? It's this list mapping from strings to numbers, and find is a linear search on that list. We could either succeed at finding it or not succeed at finding it. Since y is in this list, right, we're going to find y in this list and return the number associated with y, which is 2. So we'll go into this sum case with I equal to 2. We'll call stack lock. Ooh, what an evocative name. Stack lock on I, which is 2. That just multiplies it by 4. So then we'll fill in whatever I times 4 was, which is 8. So this is going to create this instruction that's move into EAX, whatever this thing means, this brackets ESP minus 8. Right? So that's what's going to happen as a result of running this. Okay. Now, oops, that was the wrong question. There we go. Yep. Okay, that one. Okay. So there were probably a bunch of new things that you haven't seen or haven't thought about before. I want you to just take a minute and talk about things you had to think about as you were going through that tracing that were like new or different that we haven't talked about in class or you haven't thought about before. So you can sort of mark the things that we're learning right now as opposed to things that were just like OCaml things we knew before. So take a minute, talk about it, and then we'll talk about the new things that just happened. Okay? Okay, so what are some things that are like still like what's going on here that we need to either define or talk about more in this lecture? What are some of the new things? What are some of the new things? There's several of them. So what are some of the new things? New things. You all talked about old things. New things. Yeah. Matching with a function instead of matching with. So one thing that's interesting is here, I just sort of threw an expression in between match and with, instead of just matching on some particular thing. Yeah, so if we take the sort of substitution-based way we've thought about OCaml evaluating, we can think of this find as just turns into this sum with a 2 in it, right? That's what happened during this trace. So that's kind of interesting. We didn't have, I don't think we wrote that syntax before. It does fit into our sort of substitution-based model of OCaml. What else is new? What else is new? Other new things. Yeah. The environment, what? That doesn't say environment on the screen. ENV. You want to call this, you want to say, Joe, this is short for environment. Yes, and today we will care about the environment. Other things that are new. So there's at least one other thing that's pretty new on the screen. Yeah. The sprintf is in a list, which is kind of odd. So the reason that's in a list, so that's actually, so that matches what we did on Wednesday here. And the idea is we could just like concatenate together all these strings with new lines, but it's nice to say that the compiler, this step of the compiler returns a list of instructions, just because a list is a slightly nicer, more structured thing to return. And so when an expression only needs one instruction to do its work, we'll just have it return the list containing one instruction, right? And that's what happened for primitive numbers. We just moved the number into EAX. That's also sort of what's happening for IDs. We're moving, well, something about where the ID is into EAX, right? For these operators, we would maybe have more than one instruction because we have to evaluate the argument. Yeah. So if you look at the main function that was on the handout from Wednesday, it calls a helper function called string.concat, which just inserts a new line in between each of them and then prints that string. Yep. So we're returning a list and then concatenating the other new things. Yeah. Some of these, the expert insers doesn't have a return type. Yeah, there's no return type here. That's kind of interesting. What type would I put here if I wanted to write the type in, just to be clear? What type does it return? Yeah, louder, you're right. Yeah. String list, a few people said it. Okay. Yeah, so in many cases, and I didn't talk about this in detail about OCaml, but if you've seen Haskell, this probably won't be surprising. In many cases, we can omit types in OCaml, and OCaml will figure out what type we meant. I try and put as many of the type annotations in as I can without making the code too long, because it makes the error messages better. Because if there's any mismatch, it'll like see it right next to the type annotation. But in most cases, OCaml can figure it out without a type annotation. So sometimes I leave them off. Yeah. Okay, so one more new thing. All of you are just so used to seeing this, it's like not a big deal. Right? So in this piece that was the answer, we have this new kind of thing. We haven't talked about this. What the heck does this mean? ESP minus 8? What? CSE30. Well, you didn't do necessarily x86 and CSE30, so I wanted to just like hang a lampshade on this and say what's going on here. So ESP is a register that holds the stack location, the current stack location in x86. So the current value in ESP, if you think of this in terms of like a C program running, the current value in ESP in the x86 architecture holds the sort of the current top of the stack, or the address of the current top of the stack. Okay. And also in x86, similar to probably what you've seen before, the stack grows in decreasing addresses in memory, so I'm going to draw some pictures involving ESP today, but I just wanted to make a point that what that syntax means in option B is move the value that's stored in the address ESP minus 8 into EAX. So this is doing a memory lookup, right? This is doing a memory lookup. And depending on what assembly languages you've seen before, it may have been this square bracket notation or something else, but that's what that means. You may have seen it as a separate load instruction or something similar, but that's what move does with this bracket argument as the second argument. Okay? So just to be totally clear, move EAX ESP minus 8 means put the value at the address ESP minus 8 into EAX. So we're moving something from memory into a register. Right? And this is matching some of the intuition we came up with at the end of class on Wednesday that, well, what does it mean to define a variable? It means we're going to find a spot in memory that that variable's value lives, and then we'll move things into and out of memory to represent storing to and reading from that variable. Okay. So that's the new piece of assembly we're going to use. I mean, it's not like a new concept in assembly, but it's a new piece of syntax we're going to use. And we're going to use and reuse this structure of having this environment that maps from strings to numbers. The type TENV is just a way that we can have a name for that type instead of writing string star int list over and over again. This is actually kind of a lot to write over and over again. So the type declaration just makes it so we don't have to keep copying that out. And stack lock is just a little helper. Okay, so let's talk a little bit about, actually, let's answer this second question. I think everyone's going to be able to get to this one, but let's just answer this second question quick. So answer this, this second question now, just to make sure we're all on the same page about what this code looks like and what the meaning of different parts are. Five, 4, 3, 2, 1.5, 1, 1/3. Okay, cool. All right. Yeah, so this produces an unbound identifier error where we're talking about this variable z. Z is not in the list that represents our environment, so it's an unbound identifier. Okay. So the thing I wanted to start thinking about next is, well, here I called expr2 instructions with an environment that I made up. Like I just wrote down this environment in my call to the compiler along with this little program. Really what should be happening here is somehow we construct these environments based on the let expressions we see. The let expressions should tell us, well, we're going to put these variables at different spots on the stack. And then when we go to compile the ID expressions that are in the body of the lets, then we'll be able to look up the right location. So let's talk about that a little bit. Let's talk about that. So I want you to look at the other side, the side that has the 4 boxes and the let expressions there. Okay? And the first one, so the first one is this one, the let x10 let y inc x, let z inc y, and then z. And I provided in your handout for the version of the compiler that I wrote, what instructions are spit out by the compiler that I have in mind for implementing this. What I want you to work on for a minute is let's say we ran those instructions that are there. So we're going to talk about how to implement this in a minute, but let's just say for now, this program comes in, those assembly instructions come out. What I want you to do in the little stack diagram I gave you on the right-hand side, assuming that the bottom is ESP and going up in the picture is decreasing memory locations, right? So lower addresses go up in the picture. fill in the picture with what values are going to be at different locations here, and assume that each of these, and this is because we're going to be doing 32-bit x86, each of these is 4 bytes wide. Okay? So fill in what values are going to end up on the stack after running the assembly instructions on your worksheet. Anyone need a worksheet? Anyone need a worksheet still? Uh-huh.
Does it matter that you called these all out of order than the ones you're given?
Yes, yeah, that's why I had the arrows on there, saying like, yeah, yeah, it needs to be in order.
Oh,
Yeah, yeah,
very confused.
yeah. You one of these? Okay, so what do folks think is going to be in this picture? Like, where will different values be? What values will be there? Someone get me started. Tell me which box to write write which value into. Get me started with any one of them. Yeah. So you could say the bottom box, this is where ESP minus 4 goes, and the value 10 would be there, and we could say, well, that's like where the x variable lives. Okay. And next one, yeah, 11 here, and that corresponds to y. Okay. This, and then we're going to have z be this increment on y. Okay. So all that these assembly instructions did is first move a value into EAX so we can start working with it. And then they started moving those values into memory, then back out of memory to increment them, then back into memory to save them, right? This program is like, just keeps ping-ponging back and forth between these memory locations. Interesting. So the next question is, now that you have this, there's this idea that there's these memory locations corresponding to variables. There's this idea of having this environment in the compiler that maps from names to maps from names to spots on the stack. Now, with that in mind, can you go back and fill in this case, the let case? I want you to work on this for a minute or two. Try and fill in this let case so that you'll get the behavior we just described, right? And you can sort of treat those instructions that came out as a test case for what's going to happen here. But I want you to try this for a few minutes. Try and fill in the let case with this idea that we have the environment, the idea that we have this ID case already working for us, so we just need to set up the environment to look up the right values. Try this for a minute. See if you get stuck. See if you know how to get started, and then we'll fill it in together after trying for a few minutes. Okay. And feel free to talk with the person next to you, work through this together. Mm-hmm. Doesn't it though? Yeah. So right now we're doing very sort of. Let's imagine that in the body here, instead of saying z at the end, we wrote x. Then we'd still want to be able to look up x, right? We wouldn't want to like forget about the fact that x was stored at that spot, right? And so this happens to be an example where we're using the variables right after we define them, but we might still use them much later. Does that answer your question? Yeah. Thoughts on how to get started?
So if I was one of these,
So there's going to be something that has the move with the memory address on the as the left argument.
Actually not sure how to get started.
Yeah. So so one thing to think about is what's the type of X value embodied here? What are their types?
X is a string
Mhm.
array, value is an expression, embodies an expression.
Cool. So when we had the operators where we had another expression in there, right? What did we do to work with the like that recursive case where we had that expression in there?
We kept reducing it. So
Yeah. How did we keep reducing it?
we let it do.
Yeah. What did we do with E? What did we do with E? So we compiled it so we could get the instructions for that sub-expression, right? Which is going to be a list of instructions, right? And then we use that somehow to combine with more instructions to sort of do the work of this expression. So there's a hint that we might need to call, recursively call expert to instructions on value and body, and then think about how we'll put those two together, right? Yeah, what's up? In the environment, so yeah. If we simply append it to the end of the environment, we will already have it. Yes.
And after this expression, what's the value of
X will have 5 in it. So inc just takes the, it's a really good question. So inc just takes whatever number it has as an argument and evaluates to one more than that number. It doesn't make a change to a variable.
when we discussed the function values on X?
Yeah.
Then why we need to use len here as the value of X and then change after the whole body value? Like,
Why do we need, so as a programmer, this is sort of a weird program to write. It's like declaring a constant and then never using it. But we can still imagine like compiling and running a program. Right, think about a C program where you just wrote int x equals 10 and then didn't use x after that. Right, x would still sit there on the stack. Right, so we can definitely declare variables that then we don't use.
so this is like variable declaration. This is the actual body of the function.
Exactly.
So
The
that,
actual body of the expression. Yeah, it's like the rest of the function after those declarations.
so that is not just an assignment, but it's a function.
It's a declaration. Yeah, I wouldn't call it a function. Let is a declaration. It has variable declarations followed by an expression.
Okay, thank you.
Yeah.
So in this case, so this is kind of like z is kind of like the name, and x is kind of like the value.
Yeah. Yep. What's the purpose of it? That's what the whole expression is going to evaluate. Yeah, what's the goal of all the instructions that we write? That we generate? Yeah, let me step back. When we stated our goal for the generating instructions on Wednesday, we had this sort of high-level goal for what the instructions should do. What was that? Based on what's here, what's the answer for running this program? Like, what does that whole program evaluate? And what's the final answer? Final answer. Like, what is the whole, if you take the substitution-based view of evaluation, what's the final answer that evaluates to? Which is whose value is. But what's the value in z?
It's based on whatever.
What number is the value in z?
Right here it's
So the answer to that whole program evaluating is 12. That's what gets stored in EAX at the end. So the goal of when we generate these instructions is to store the answer for the whole expression in EAX. And that's why we need the body, because that's the thing that talks about what the final answer is. Ideas here? Okay, so you're definitely doing recursive calls, right? So doing a recursive call on body, right? And in body, you were adding something. You're trying to add something about value to the environment, right? That makes sense, right? I like that. It's worth thinking about what type the environment has, so you can think about what you'll be sort of linking on to the beginning of that linked list. Because value has type expression. So we want to be putting some mapping from a name to some integer that tells us where on the stack to look. Right? So, well, what type is value based on looking at our type declaration here? Yeah. So we might need to get if we think about this example, and think about which instructions came from 10, which instructions came from inc X, which instructions came from inc Y, right? And those must have been generated by compiling that sub-expression. Uh-huh. Yeah. Okay, cool. So I see lots of people doing this in a couple different ways. This is pretty cool. All right. Let me quickly draw a picture that I think will be useful for stepping through the implementation of this. Okay. I want to get the assembly instructions for this up here and talk about, do another color coding where we talk about which assembly instructions correspond to which part of this expression, right? How is this generated? So we had move EAX 10. And that's pretty clear. That instruction corresponds to this 10, right? That's what that corresponds to. Then we had the next instruction here was move into ESP minus 4, the value in EAX. What part of the expression does that correspond to? Like what part of the expression on the left-hand side is that? Sort of like the first let x, right? This corresponds to this part where we're saying like, well, we want to assign whatever value we got from evaluating the 10 expression, that's going to go into x. And we said x is going to end up at this ESP minus 4 location, so that's what maps there. The next instructions we have are move. Well, this seems, someone pointed out that this seems kind of funny to be doing this right after we moved this value into memory. Now we're moving it back out of memory into where it was before. But the next two instructions are add EAX 1 along with that move. And these two correspond to this expression here. Where the first instruction is coming, we know the first instruction from what we said before is coming from looking up the value of x, right? This means look up the value of x. And then this, we know from what we saw on Wednesday, is coming from the increment expression, right? So the two instructions here are generated by saying, well, how do we get the value of x into EAX, and then how do we increment it? And then the instruction after that is another move. This one into ESP minus 8, moving that incremented value into ESP minus 8. and that is what corresponds to setting this whole thing equal to y. So what's happening here is we're evaluating the thing that comes after the name in the let expression. In the homework, we're calling this part of the let expression, we're calling the binding, which is where we're declaring this variable. So this is the name of the variable we're declaring, and then an expression for what its value is going to be. So we're doing those two pieces, evaluating what the expression for the variable's value, then storing that value into memory. Then we're going on with the body of the let expression. So in this case, this is the whole body of that outer let expression. And that's what we're repeating every time we do a let. And so we can sort of color the the instructions that come out with what instruction they came from in the input. One interesting question here is somehow we knew that y was going to be at -8 while x was going to be at -4. Do we know, like, that is something to think about when we go to implement this, right? Like, how did we know that x was supposed to be at 4 and y was supposed to be at -8 and that the next variable is supposed to be at -12? Right? How are we gonna figure that out? Right? So that's something interesting about this. The rest of it, right, the idea that I just talked about of having the evaluation of the value for x, then the storage, and then the body, that's more like things we've seen before where we want to get the instructions for these two sub-expressions and put them together somehow. So let's put some of this together into a couple ideas. Now, we know that we're going to want to call, I'm going to call it VIS for the value instructions. We know that we're going to want to call expr to instructions on the value part. We need to get the instructions out for this expression because that's how we knew that we would get this this moving 10 instruction. That was basically the first case that would correspond to value. Now, we have these other two parameters to expr to instructions now. We have these other two parameters. And in fact, one of them we didn't really talk about, this SI one. What the heck is that, right? But we talked about the environment one. So the way to think about these two things, the way to think about SI and the environment, is that every time we go into a let body, every time we are going to define a new variable with let and then start evaluating things in its body, we know that we need to start using a new location on the stack to store things, because the location on the stack that we're sort of currently looking at, the current top of the stack, is going to need to be used for storing this current variable that we're looking at. So we know that when we store something in X, we're going to use this current location on the stack, the sort of bottommost one, ESP-4. And when we go into the body of this let, we need to start using addresses that subtract more. We need to use that free space that we have available growing upwards in the picture. And that's what this parameter stack index is for. It's going to keep track of sort of how many variables we've declared, how deep we are in the stack, so that we can keep looking at fresh space every time we do a nested expression. Okay. So when we go to compile the sort of the value for this binding, the value that corresponds to x, we're not using any more space. Whatever happens when we're compiling the binding for x, we're not using x yet. So we can stay at the same stack index here. And we haven't added x to the environment yet. So we can use whatever environment we had before. Okay. This really is just saying, I need the instructions that are going to calculate the value here and store it in EAX for what x is going to get as its final answer. Now, this instruction here, the one where we take the current value of EAX and store it onto the stack, that instruction needs to be generated here when we do this let expression. The let expression's job is to do this storage. So that instruction had better be happening. We'd better be creating that during the let, right? Sort of while we're figuring out what to do with this let. So here we're going to say, I'm just going to give it a name. I'm going to call it let store x. And this is going to be a single instruction. So again, I'm going to write it as a list, but it's going to be a single instruction. And we sort of know from what we see here that it's going to have to be a move into memory. Right? We're going to move something into memory. And I'm going to fill it in with an integer. We know that when we run this, we're going to have the value that we want in EAX, because that's always what these instructions are going to do. So this is the instruction to store the x value into memory. Yep. And I'm going to leave blank here because I want to ask you this in a minute. What we're going to put as that value, how we're going to fill in that value there. Okay. And then we're going to have some instructions for the body. We know we need to recursively call generating the instructions for the body. We know we need to do that. And this is where we need to put a little more thought into what's going to be for what we're going to use for the stack index in this recursive call and the environment in this recursive call. And then after we do these, right, once we fill in these blanks with things that make sense for us, then we can just put these things together, because each one of these let expressions is going to be a set of instructions that calculate the answer for value, then store it, then we're going to have the instructions for body. So at the end of this, what we need is the value instructions followed by the instruction that stores the value in the right place for x, followed by the body instructions. That's going to be the final list of instructions that we need to generate in order to evaluate this, in order to get this whole let compiled. And the thing that we need to figure out is how to use this new machinery, this stack index and this environment, to fill in the right spot for storage and to do the right thing in the recursive call for the body. Because when we compile the body, we need to keep track of the fact that now we have this new variable available. So any EID expression that appears in the body needs to be able to look up that variable at the right spot. So with this skeleton now, right, I want you to think a little bit more about what's going to go in the 3 blanks that are left in this skeleton. What's going to go in those 3 blanks? Okay? So think about this for a few minutes. I'm going to come around and just see what folks are up to. Then we'll go over the rest of this together. So the thing I'll point out here, think about the type of this tuple relative to the type that the environment's supposed to be. Think about that, right? Because there's a little type error in your program. It's exactly the right sort of idea, but there's a type error in your program, and it's an interesting type error. Ideas? Uh-huh. Mm-hmm. Okay. Yeah, that's worth thinking about. And you might be able to use the type to help, right? If you look at the type that the environments are supposed to be, you know you need a string and an int. So what does that mean, right? And you can also think about the examples we had at the beginning where we successfully looked something up. So what does that mean for what we need to do? All right, I'm going to go over this, sorry. Okay, so let's talk about filling in the rest of this, implementation. So I think that it's it's pretty useful to talk about the recursive call first. So I want to focus on these bottom two blanks first. So here and here, this is the recursive stack index argument, and this is the recursive end argument. So what did people think of for the way to use the recursive stack index argument? What did people have for this sort of the blank for the first arrow here? This is the new value for SI in a recursive call. What do people have as a suggestion for that? Yeah. SI plus 1, SI plus 1. Since we have this helper function that's multiplying by 4, we don't have to necessarily think about, you're saying we're going to go sort of 4 chunks at a time because we have this helper function that multiplies by 4, and you're saying we want plus 1 here. Did anyone do anything other than plus 1 here, though? Yeah. You just went with SI? Okay. Other things that people did here for this recursive call? Okay, so SI versus SI plus 1. I'm going to put in SI plus 1. I'm going to leave SI as a, so we maybe could talk about the consequences of just doing SI. We don't have a lot of time left, so I'm going to press on. That's an interesting idea. For the second spot, what did you put? For the second spot here, this second blank for the recursive use of environment, what did you put? Yeah, go ahead. Okay. So you said, I'm going to add something new at the beginning of environment, right, at the beginning of the environment list, that is a mapping between whatever name we had for this variable and the current stack index, okay? Anyone have anything else? Anything else for this case? Yeah. Uh-huh. Okay, so you're making a comment that, well, there's examples we haven't thought about where we try to define the same variable name twice, right? Like if we had let z 10, and then in the body we said let z 11, what should z be? And you might do something with env right here to make a decision about that. Other ideas that people had for this recursive call, this recursive use of environment? Any other ideas? So this is a reasonable idea, and it's the way I wrote it. There's a couple other things. There's a couple little off by one kinds of things you could do depending on how you set this up. But this is the way I wrote it. So what this is saying is, as we traverse through let expressions, the stack index is going to store where we are right now. How deep inside nested let expressions are we, to make sure that each body we have a space for one more binding now, right? Space for one more. So we're going to increment by 1 in body, and then every time we go into the body, we're going to say, well, the place we stored the current name is whatever we had as the current stack index. With that choice that says that x comma si is going to be what we look up when we look for this identifier in the future, what does that mean for this other blank here? What does that mean for this blank that we had? What should we put here if we have x comma si below? Yeah. Just SI? Just SI? Other suggestions? A bunch of people said, okay, so stack location of SI. So basically SI, but SI times 4 because we want to make sure we're using the right sort of by 4 bytes lookup. And this is going to go directly into the integer position that we're looking up here. So here we'd want to match, because this matches the use of stack lock in when we look up the identifier. So we want to make sure we store it to exactly the spot where we're going to look it up. Okay. So we should put it at the spot in memory that corresponds to that slot that we have. Okay. And so with that, so let me just make this pretty, right? Put this in the right spot. So with that, this actually, if we type this in, this would give us a working implementation of defining these variables and then later looking them up. Yeah? Oh, SI, thank you. I just used the wrong variable name.